Good morning, everyone, and welcome to the third day of Nobel Lecture Series. It is my pleasure to introduce our speaker of this year, again, Dr. David Tarasick, renowned atmospheric scientist and co-discoverer of 2011 Arctic ozone hole. Dr. Tarasick's scientific journey highlights challenges scientists sometimes face when trying to share their research, particularly in the field of environmental and climate sciences. In 2011, he became famous as an example of muzzling of scientists. After the discovery of Arctic ozone hole, he was prevented by the government of the time from speaking to science journalists for several months. After intense public pressure and parliamentary discussions, the silence lifted, allowing him and his science to be heard again. His story also shows that the fame can come in unexpected ways. As his mother told him, "When you were a little boy, I knew that you would be famous someday, but I never imagined it would be for not talking to people." Fortunately, today, Dr. Tarasick has the floor. He will be sharing his expertise in a lecture titled Stratospheric Ozone Science, a success story with new challenges. Let's once again welcome Dr. David Tarasick to share some of his knowledge with us.
Thank you very much. Okay, thank you very much for that excellent introduction. I could add to that story a little bit because the government actually was at the time trying to reduce or even shut down our ozone research program. They picked a really bad time to do it because, of course, the atmosphere conveniently produced a dramatic event, the ozone hole. So the end result was they're trying to keep this message down. So, and nothing to see here, move on, please. And meanwhile, we were being discussed in Parliament almost every day. So for 2 months, we didn't know if we'd have jobs next week, but every morning we came into the office and the first thing we did was to check Hansard, the official record of parliamentary procedure, to see if we'd been talked about yesterday. But most days we had. And so it was kind of mixed feelings about that. It was kind of tense, but it was great fun. So I've got a few things to illustrate my title slide here. You can see pictures from OMI, one of the ozone satellites. There's a typical year, 2010. Lots of red there, which indicates high ozone. And then in 2011, very low ozone, so severe depletion in the Arctic spring. These are March images. And here in 2020, even larger and deeper. And then, yes, a couple of other interesting things, because I'm going to talk a bit about dynamics and a bit about chemistry. So this is from a paper that Jane Liu did. Jane's is a professor in the geography department, but she's really a physicist. She worked with Dylan and with me. And this is looking at tropopause changes over the past 40 years, tropopause height changes, which of course are due to global warming, but they affect the stratosphere because that sits on top of the tropopause. And then this is from a very recent paper, I don't think it's published yet, by Paul Newman, showing that last year ozone bounced right back to pre-1980 levels, which is interesting. So we're going to be talking about ozone up here in the stratosphere, the ozone layer, and I remind you that the ozone is the reason we have a stratosphere, not the other way around. So when we say the ozone layers in the stratosphere, in a way, we're putting the cart before the horse. Ozone is important for the critical for the actual temperature structure of the atmosphere. There are There's a lot of dynamics involved in the distribution of ozone in the atmosphere. And so this is just to remind you of that. We have the Brewer-Dobson circulation causes ozone to build up towards the over the winter towards the spring. And so we have more in the springtime up here in Northern Hemisphere springtime. And we and the same down here. This is pre-1980, so you don't see the effect of the ozone hole. And these graphs show that ozone correlates very well with temperature and with this measure of the dynamical transport of heat, the eddy heat flux. And that will be useful to look at later. So that's really just an illustration of the fact that it is the wave-driven circulation that's pushing the ozone towards the poles. Another an interesting example of dynamics, we sometimes see events like this. This is a meteorological front passing over our Brewer station in Montreal, and the height of the tropopause is measured by the McGill radar. And what you can see is that they correlate very well. So unfortunately, this didn't turn out to be a terribly good predictive method. A lot of people have tried over many decades because these relationships are common, but it's more complicated and it's not very consistent. So I had a postdoc working on that for a while too, but we gave up. You sometimes see really nice events like this. Ozone goes way up when the front passes over, and vice versa, but not all the time. Now, of course, everybody knows that chemistry is involved. So this is my one slide on chemistry, all of stratospheric chemistry gathered into one slide. So it's a little bit oversimplified. I'm sure the chemists in the audience are appalled, but this is a physicist version of stratospheric chemistry. Basically, this is the main production method. Ultraviolet radiation breaks up oxygen molecules. Some of those odd oxygen atoms attach themselves to another oxygen, become ozone. And there are a variety of loss reactions up here, which are really of the same form. There are a variety of species, chlorine, bromine, nitric oxide, can act in this way where they oxidize by ozone, and then they are recycled. That's the critical bit. That's why it's a catalytic cycle. Otherwise, there wouldn't be enough chlorine to make a difference to the ozone, but each chlorine gets recycled and goes back and does this again. And that happens very rapidly in the polar spring, and it happens to some extent over our heads. And as I described in the first lecture, there was a lot of concern about that in the 70s. And then it turned out, somewhat to everyone's surprise, that these reactions were more important. And that when chlorine monoxide reacted with nitrogen dioxide, you ended up with chlorine nitrate, which was very stable. And also with OH, you get hydrochloric acid. And those turned out to be reservoir species. So all the chlorine was being held in reservoir species. And then we had the ozone hole. So this is one of the first pictures from 1985. And it was with surprising rapidity. It was determined that these reactions were happening in cold, dark conditions of the Antarctic night. So most of you knew that already, but I just wanted to reiterate. So this was the picture we ended up with globally at about the time that the Montreal Protocol provisions started to come into effect. The chlorine starts to drop after about the end of the 20th century, 97, 98. You have considerable change in, this represents about a 7% change in UV over our heads. Here, of course, in the Antarctic, it's larger. Modest, but still quite significant when you consider the number of skin cancer cases you might get out of that. So the fact that we halted this is a testament to the effectiveness of the Montreal Protocol. It's often described as the most successful environmental treaty ever made. And of course, many of you will know that there was an attempt to model the Kyoto Protocol along the same lines. Get everybody to agree to modest reductions, but make the revisions, mandate that there will be revisions to those reductions based on revisions to the science. So the Montreal Protocol and the Vienna Convention, in which it's part of, mandate quadrennial assessments of the state of ozone science. And this is critical because initially there wasn't the reductions that were called for by the treaty that was signed in 1987 were about 3%. They wouldn't have made a huge difference to the ozone layer. But because the science came in and said, no, we need to do more, we need to do more, well, everybody was now on board. And and it's still going on, I should mention. Most recently, the Kigali Amendment has called for the reduction and elimination of hydrofluorocarbons, which are CFC substitutes. So you can see that from this graph. This is a prediction of, this is what would have happened with the original Montreal Protocol reductions of about 3%. But subsequent amendments based on stronger, more definitive scientific conclusions led to the reduction, much stronger reductions by 1990 in London, and eventually the complete elimination of CFCs from the 1992 amendments. And it's working. I got these graphs from Jason and Kaylee's group. These are ACE measurements of, this is CFC 11, this one's CFC 12, and you can see they're falling off pretty much as we would expect, with a little bump here, which was interestingly detected by global observations. And when the Chinese government was contacted about the fact that these extra emissions, you can see the curve kind of flattens here for a few years. They reacted very quickly and shut down the illegal CFC factories, and then we go back down. So, highly successful. So successful, perhaps, that actually nobody much under the age of 50 seems to remember. And that's really it kind of bugs us because, we saved the world and nobody knows. So now we're writing papers that say, look people, see what would have happened if we hadn't done this. And so there are quite a few papers called World Avoided, just to make the point that, yeah, it wasn't all foolishness. It was, we actually did make important changes to the atmosphere, and the Montreal Protocol is really important today. So you can see well, you can read the graph. You can see what would have happened to ozone. It would have fallen off a cliff, and UV would have gone to levels that we have never experienced, at least except for those of us who've flown above the atmosphere. There's actually a photographic window in the space shuttle, which is quartz and emits UV transmission. It's there so that you can take photographs at high at shorter wavelengths, but it's really dangerous and has to be kept covered because the astronauts would get badly burned from exposure to solar UV coming through the quartz window. we had an experiment in the 90s where we made observations through that window, and there's a special cone that you put around the window to make sure that there isn't too much light that gets through there, that it all goes into your instrument and the astronaut isn't exposed. Okay. But there's also been some interesting developments. The atmosphere is always fun. It never just does what you expect. Every time you think you figured it out, it throws something else at you, and that's exactly what happened here in 2011, here, and in 2020. But a typical year looks like this. No significant depletion in the spring. These are all spring images. Now in 2011, which of course caused all the kerfuffle that we spoke about at the beginning, there was quite significant depletion, and these are what I'm showing on the left are a lot of profiles from our station in Eureka that many of you actually I think have been to. And you can see there's quite a bite out of most of the profiles at around 20 kilometers. But it doesn't really look like the typical Antarctic grouping of profiles that I have on the right. You can see that in the Antarctic, during the depths of depletion, there's essentially ozone goes below a detectable level for quite a vertical distance. So, I mean, this is very significant depletion. It's about 50%, I think, if I remember correctly. But it's nothing like this. This is so people said, oh, it's not really an ozone hole, but some of us preferred to call it that. It was anyway. So in 2020, it looks a lot different. You can see here, this is an ensemble of all the profiles from Eureka on the left. I took some of the more dramatic ones and an overall average on the plot on the right. The black line is the long-term average, what we would expect to see without severe depletion at this time of year. The red line is the average from 2011, and you can see that this differs quite dramatically in 2020. And we saw losses greater than 95%. I think I've written that at the top there, yeah. Down to essentially though 128 ppb. That's typical levels for the upper troposphere. It's really really low for the stratosphere. Stratospheric levels measure in parts per million. Okay. And similar results from our two other sites that were in the high Arctic, which Alert and Resolute. And again, I'm just showing some of the profiles because the original slide's too busy. Now this is an analysis from the match group with sort of all the sondes together. Most of them are ours actually. And essentially the same conclusions. Values as low as 125 parts per billion, which is extremely low for the stratosphere, and they're typical of the Antarctic ozone hole. So plotting some of those minimum values together, you can see on the light gray dots are values from other years for the Arctic. The dark gray dots, all these ones that cluster down here, those are from the Antarctic, and the red and blue are 2011 and or 2020 and 2011. So you can see that in 2020 we're in the Antarctic, well down comfortably in the Antarctic range. And if you look at data from the microwaves limb sounder, it's a little less scattered, and because there's more averaging, but it shows the same thing. And then this is an analysis from the group at Bremen using a chemical transport model and a little more precision on average levels, but again, the same conclusion. Losses, extreme losses, quite different from anything we'd seen before. So why are we seeing this now? I mean, chlorine's going down. It's dropped by about 25% from the peak in 1997, 98. Well, it appears that the stratosphere, at least at times, is becoming colder, and we're seeing very low temperatures, at times approaching the typical envelope here in the dark gray for Antarctic temperatures within the vortex. So we are getting more polar stratospheric clouds, and they're lasting longer. So there's more chemical processing and therefore more chlorine released. And of course, in the Arctic, because of the fact that the Arctic vortex is unsteady, it doesn't all happen at once. It happens somewhat throughout the spring because parts of the vortex wander in and out of sunlight. So I've shown this is the temperature for formation of nitric acid trihydrate ice clouds, which are the primary surface for the heterogeneous reactions that I discussed earlier. So a little more backup from MLS, just demonstrating that what we think is happening is actually happening. You can see, let's see, at the top, you can see evidence of denitrification. So nitrate is being taken out of the atmosphere, which means it can't go back into chlorine nitrate. The nitric acid is also coming out of the atmosphere. You've got low hydrochloric acid, which means that most of the chlorine is available in active forms, such as ClO down here. So more ClO and less of the reservoir species. And the model shows the same thing. Chlorine, the chlorine deactivation, the chlorine collection into reservoir species was much lower, and the depletion rates in the graph here much larger and lasting longer. That's a critical thing about the 2020 hole. It lasted a long time. And when the match guys do their matching of air parcels, you get this fairly nice linear relationship with time spent in sunlight and the loss of ozone concentration in air parcels. In fact, in the paper, we stated that if this had continued for 2 more days, we would have, this actually projects to 0 within 2 more days. So typically, I think I've written that all there. Yeah, the Arctic sees a lot less chemical depletion because it's much more disturbed by planetary waves, though, which have to do with the fact that there's a lot more land in the northern hemisphere. And so we don't tend to see this kind of chemical depletion. It tends to be warmer, also because of the larger heat transport. And but in 2020, it was quite severe. The vortex was unusually stable and quite cold. In fact, it was the strongest and most persistently cold in 40 years of measurements. Wave activity was weak, and there was an unusual situation where the vortex was strong enough that waves were actually reflected. An interesting paper from Lawrence et al. Discussing this in great detail if you're interested in the dynamics. But the waves were strong enough that the waves impinging, or sorry, the vortex motion was strong enough, the winds were strong enough that the waves were unable to propagate into the vortex in some circumstances, and so are reflected. I like that because I worked on that with my for my PhD. I did waves, and it was fun. So also the Arctic oscillation was the largest on record. So back to what would have happened if we hadn't had the Montreal Protocol. Let's check that. Yeah. Just a few remarks about whether this is an ozone hole or not, because some people will bite your head off if you call it an ozone hole. It's really, well, the conditions were similar to an Antarctic ozone hole. It doesn't rank very high compared to the Antarctic. The total area was only about 5% of the typical area of the Antarctic ozone hole, and it didn't last quite as long. Nevertheless, if we hadn't controlled CFCs, here's a model study looking at what would have happened if chlorine levels had been what they were in 2000, or indeed had increased by a few percent as they had been previous to that. On the right, here's a simulation using the Wacom model. Simulation of 2020 conditions, and there's measurements just to show the model does a good job. Okay, measurements from the satellite, there's the simulation. Now, if we put the levels of chlorine that we would have seen without the Montreal Protocol, we do have a large ozone hole, very similar to the Antarctic. And the difference amounts to as much as 130 Dobson units, which is enormous when you consider that the average amounts are, 300 to 400. Yeah. Oh, and the area of this would be, oops, darn. The area of this would be similar to what we see in the Antarctic. That's the other point I wanted to make. This is really showing the same thing, or in a different way. These are minimum levels throughout the year. This is what we would have seen. This is what we in fact saw because of the Montreal Protocol. So we're turning again to the question of why we're seeing this now. 2020 is the coldest Antarctic winter that we have seen since the start of reliable observations. It would seem evident that this is a result of climate change. Climate change is cooling the stratosphere at the same time as it warms the troposphere. It's also raising the tropopause because of both of those effects. So there are dynamical changes happening. Climate change also increases the dynamic variability. Much the same argument for why we think we're seeing more hurricanes and storms, because essentially, if you're the analogy I like to use is if you've got a pot on the stove and you turn up the heat a little bit, it boils more furiously. The Brewer-Dobson circulation is stronger, the waves are stronger. So not only does it tend on average to get warmer, but things also oscillate more. There are larger changes. So even though chlorine's going down, we've had some very cold winters, and 2020 is the coldest so far. Nevertheless, we do expect ozone levels to go back to normal in the long run. The ozone depletion is not really increasing. However, we're not really seeing recovery yet. There's a lot of attempts to find it, and I'll show some plots of it I think, or I showed one yesterday, of changes at high levels, 40 plus kilometers. But this is an average of our ozone sonde data, and you can see that in the lower stratosphere, the trends are still, up until 2018, are statistically significant and negative. And there's some other papers showing the same thing, including Joey's paper for using the trajectory mapped ozone sonde data. This probably has a lot to do with dynamic changes in the atmosphere. This is from a paper by Jane Liu's group in geography here. The tropopause has been rising fairly steadily over the past 40 years. As I explained from that first graph, if the tropopause height goes up, you think of a very simple model of the atmosphere where we have not too much ozone in the troposphere, a lot of ozone in the stratosphere. If you raise that tropopause, the ozone in the stratosphere tends to slosh away somewhere else. In any case, your stratosphere is thinner, and therefore the total amount is less. So as the tropopause rises, you would expect to see, all other things being equal, you would expect to see less ozone in the stratosphere. The stratosphere is also cooling, which has an effect on temperatures and therefore the formation of polar stratospheric clouds, as I was saying. Okay. And indeed, I found a recent paper that demonstrates these effects in a more sophisticated way with a chemical transport model. Yeah, this is looking at trends from the let's see, the plot here is without taking the new dynamical effects into account. You see that the change in trends from pre-1996, so before the peak of stratospheric chlorine, the trends are strong negative over the 20-year period previous to that. And if you look at the trends after that, they're mostly small, hard to, but statistically at the 95% level, they're significantly different from the pre-1995 trends. So before the peak of chlorine, you've got strong negative trends. Afterwards, you've got very modest trends. And if you take dynamical effects into account, this pink line now agrees with what we see from a number of different satellites. The argument is simply that we do understand what's going on, and the fact that we haven't yet seen complete turnaround is not a surprise. And then Paul Newman published this paper, or has almost published this paper. I think it's still in production, showing that last year ozone bounced back. That's of course more a demonstration of atmospheric variability, but it is encouraging. Things are on the right track, and you can see from this graph that it's dynamical primarily. There were a lot more waves last year. Okay, I'm getting low on time. Okay, I'd also like to talk quickly about something we've been doing, because I'm actually still working on this, trying to improve the long-term stability of our ozone sonde record. We've done a lot of work comparing with satellite records and comparing other ozone sonde records, and we found a mysterious drop-off Some of you may have heard of this. We published a couple of papers saying this is going on and we don't understand it. Not a very satisfactory thing to write in a paper, so we've been trying to understand it. And this slide shows essentially what we're seeing. There's a fair bit of difference when you compare your results, the integrated ozone sonde results with satellites. These are comparisons with OMI. I've done some averaging here. These are the averages for the for the sonde. What am I looking at here? Mixing ratio. Oh, sorry, no, just the differences. Yeah, this is just the differences. So they average around 0 here, up to around 2014. And then there is this drop on average. And then we switched manufacturers and it goes back. So there's something with the instrument that happened around 2014. And it actually appears to be about serial number 25,000. So I looked at a lot of different parameters. Unfortunately, with ozone sondes, you don't have a lot of other housekeeping data like you have with a satellite instrument. You can't look and see whether it got too warm or the motor current was low or the battery ran out. But there's a lot of ancillary information that you can derive from the record. So I tried to look at everything I could. And most of it was inconclusive initially, but what was clear right away was that if you simply looked at the volume mixing ratio the sondes were measuring, it was clear that there was a change, because this is quite independent of satellite comparisons. There's volume mixing, the mixing ratio measured at 10 mil, I think this one's, yes, 10 hectopascals, drops by about the same amount as we were seeing in the comparison with satellites, with OMI, and then bounces back after we change to science pump. So it's not a satellite artifact, which of course was the first thing we thought. Satellites are wrong. Of course, we're right. After all, they use our sondes to check the satellites all the time. So, but the thing that stood out the most was this parameter where you measure the time that it takes the sonde to pump 100 milliliters of air. It's part of the preparation procedure and it's recorded. And there was a change at all of our sites. In Canada, we have the advantage that we have about 8 sites where we're flying ozone sondes that are prepared in the same way with exactly the same procedures by generally the same people. And so the one thing that stands out a little bit is that, with the exception of Churchill, this station 77 is Churchill, there is a jump in the time that it took to pump 100 milliliters of air. It doesn't seem like much, but it was the most consistent thing I found. And I also knew that at Churchill, we'd had some problems with the operator. A lot of this, for almost 2 years, there seemed to be issues with too many flights not being successful. So I'm kind of putting Churchill in its own box, which helps this analysis. Well, a bit of serendipity perhaps, but when the Japanese do things, they do things really well. And there's always been an issue with how much do the pumps vary on the ozone sondes. It's too much work to calibrate every ozone sonde before you fly it. This takes a couple of hours. Well, they built an automatic apparatus to measure the pump efficiency, and they installed it at 3 of their stations. And they started doing this in 2009, and they were flying the same type of sondes. And they got these very interesting results that there was a jump in the pump efficiency. And we know that they changed the motor, because the motor in the ECC sonde until 2013 or so was the motor from the Sony Walkman. And Sony stopped producing the Walkmans. So they had to find a substitute. And this is what it did to our atmospheric measurements. This is Sony's fault. Anyway, very similar jumps at other pressures. And when I looked at them in detail, they had 3 stations where the Japanese were doing this. And there's a fair bit of variance between stations. But if I look at our comparisons to MLS, the differences fall almost precisely on this kind of curve. So I look at that and I say, yes, it's obviously a pump issue. And once again, Churchill's an outlier, but anyway, if I make correction for that jump, I can take the average jump from the Japanese series. Now, it's not going to be precisely what we would have, because as I showed, there's some differences between stations. So if we had measured our pumps, they would probably be a bit different. But nonetheless, if I use their average amount, it removes most of the difference with the satellite comparisons here. The ones that are highlighted are the ones that are significant at the 2 sigma level. So if they're not highlighted, they're arguably not important. And on average, the drop-off is now quite small. But still significant on average. Still on average negative. Now, but another thing I noticed was that the changes with OMI seemed to be larger. So I'd heard some rumors that there was a contention, there were some issues with OMI. So I talked to a colleague of mine at Gord Lebeau, and he said, oh yeah, there's been a 1% change in OMI at around the same period, oddly enough. And that's the graph that he sent me showing, and you can see there's about a 1% change in the OMI response. And if I take that into my calculations, the average drop-off is very, very small, quite negligible. In fact, the differences vary between plus 2.4% and minus 2.1%. So we are right where we want to be. So final slide. The success of the Montreal Protocol means that we expect that ozone depleting substances in the atmosphere will continue to decline, and stratospheric ozone will slowly recover. But we don't see this in the data yet, and climate change may throw a spanner in that. We may see future Arctic ozone holes. There's also an issue potentially for the ozone layer with climate mitigation, putting aerosols in the stratosphere. We know from volcanic eruptions in the past that there is some loss of ozone on sulfate aerosols. Not large, but some. There's also a lot of concern about rocket exhaust. The number of rocket launches is expected to increase by orders of magnitude over the next few decades. And so we really haven't done a lot of work on what that may do. And I want to make the point that we need to keep looking at our ozone sonde record, since it's being used in so many ways to put together satellite records, to validate or evaluate the quality of other instruments. And I think this needs to be an even larger priority than it has been. And comparing with multiple satellite sensors seems to be a really good technique. The fact that we have a number of different instruments measuring, in principle, the same thing means that you compare to 5 different satellites and they all say that this, well, it's pretty hard to blame it on the satellites, and vice versa. And I like to end with that one. It's a big.
Okay, thank you for the great talk. Does anyone have any questions or comments, I suppose, as the slide is asking for?
David, in one of your earlier slides, you had a plot showing the trend in UV radiation as a function of latitude, right? And so there were positive trends in the high latitudes. This was before the reversal in chlorine, I think, right? I think it was right. In the tropics, I think there were some negative trends, if I remember correctly.
Well, let's see.
I remember it was pretty early in the talk.
I don't imagine that they were
if they're statistically
significant.
Okay, they probably were.
But the tropics have confused ozone scientists for quite a long time, as I'm sure you know. Where were we? Yeah.
Oh, okay. Yeah. So they're probably
not. Yeah, they are slightly negative, not significant, at least at the 2 sigma level. But I believe these are 2 sigma error bars. However, with changes in the Brewer-Dobson circulation, you can get more or less ozone over the tropics.
Yeah, that's what I was wondering, if it's dynamical or chemical. I couldn't imagine how the chemistry could lead to, because that would suggest more ozone, a larger ozone column to give you a reduction in UV radiation, right?
Mm-hmm.
Yeah. Okay.
This is because of the reduction in the ozone column, and there wouldn't be. I mean, is there any in the tropics? I think there might be a small reduction of the ozone column in the tropics. Even you wouldn't expect much because you've got so much production and loss happening at 40 kilometers. But what really matters is the ozone that's lower down, and that's got to have had a more complex circulation.
Okay, I'm struggling with the direction of this. Okay, so you have a negative.
This is going up because it's UV. Ozone's gone down. If we were looking at total ozone changes, we basically take this graph and flip it upside down.
Right. That's exactly right.
Yeah.
Yeah. Right.
So this represents the large losses around the Antarctica.
And so you're seeing some slight increases within the tropics for ozone that is giving you this reduction in radiation, right?
I would think that that's what that means,
Right.
but I honestly don't.
Okay.
Haven't looked at the tropics much.
Okay.
In fact, we were actively discouraged from looking at anything much outside Canada since when I worked for Environment Canada.
Any more?
Thanks. So you were talking at the end about the correction you needed to make for the pump speed. So was this essentially a correction to the average, like the smoothing and the vertical? What about the pump speed affected the ozone?
Well, the amount of ozone you calculate is dependent on your pump speed. But normally you take a measure, invariably you take a measurement of that before you launch the sonde of the pumping rate at the ground. But you're assuming that the change in pumping rate as the sonde rises, as the pressure changes, the change in pump rate follows the same curve for every instrument. It doesn't. exactly. But it's generally considered too much effort to measure each pump before you launch, because you have to have a pressure chamber, and you have to spend a couple of hours to measure the change in pumping rate with outside pressure. So we're looking, so there's the measurement at the ground, which in fact calibrates overall the pump. But the change of pumping efficiency with pressure or with altitude is something we don't generally measure. And what the Japanese did was they made it something that would automatically do this for every sonde. So you could put your sonde in this, and it would inflate a balloon and inside a bell jar, something like that, and make that calibration curve for you. For virtually all the stations in the world, we use an average calibration curve that's been determined from various experiments in chambers and laboratories. And there is a variation of a few percent. So once we realized from looking at the MLS data that this looked like a pump correction curve. I was pretty sure it had to be something with the pumps. But then this paper came out from the Japanese, and we went, well, isn't this nice? It shows exactly what I wanted to hypothesize. So we're pretty sure that this is what has going on, certain enough to make the correction.
And,
Great, thank you for the talk. In 2020, when you were seeing those really cold stratospheric temperatures in the ozone hole, we were still like the chlorine levels are still above what they were in like 1980.
Mm-hmm.
Is it ever the case where like, do you need high chlorine still to get those ozone holes, or could you get temperatures that are cold enough where you would have some reduction of ozone even with chlorine levels like back where they were?
Depends why it's cold. I mean, you would have the heat, as I showed from a couple of plots where I showed the eddy heat flux, the way the wave-driven Brewer-Dobson circulation, the planetary waves are pushing ozone towards the poles. They're also pumping heat, so you tend to have more ozone and a warmer polar stratosphere if the Brewer-Dobson circulation is more active, and it does vary from year to year, and it does vary with climate change. A number of papers showing that it's definitely strengthened over the past few decades. So, but if you have a year when you have a really cold vortex, you will have low ozone, just for that reason. But nothing like what we see with the heterogeneous depletion, chemical depletion.
and we've actually got time for. Oh.
Since this slide is still up, sorry, it just got me thinking. So I know if you look at the ozone profiles in the lowermost stratosphere, you tend to see this laminar structure. You have to get these layers that are formed sometimes, so which I think are associated with synoptic wave activity, right?
Yeah, Rossby waves usually, planetary waves.
Right. So has anyone looked at whether there have been trends in the laminae structure over this time period? Because that might tell you something as to whether what you're seeing is a dynamical effect on transport of ozone out of the tropics in the lowermost stratosphere.
I did a paper on that years ago. Yeah, it worked for a while. I got really good correlation between essentially counting the number of laminae as a measure of the wave activity. But then it seemed like the more data I added, the less less significant the correlation was. So
Okay.
I haven't looked at it in a long time.
Okay.
And any more? We'll actually. Okay. Well, that's just 12. So we'll thank David again.
Oh.
And I want to remind everyone that the lunches that are on the sign up online, Thursday and Friday both have, today's Thursday, today and tomorrow both have 2 additional slots. I think they were filled up before, but now there's, I think both of them have 2 slots available. So if anyone wants to come to lunch today or tomorrow, I guess within the next couple of minutes you can sign up and then follow us. Okay. Anyway, thank you all for coming, and see you tomorrow for the final lecture. Is that everything?
Sorry?
Is that everything?
Yes.